Hello, so this is going to be the first lecture for chapter number 3. And so before we get into some new material, I want to make sure that we've practiced our naming. All right, so we're going to do a little bit of review, and then we'll get into some more new material. Chapter 3 is kind of focusing a little bit about our molecules coming together. So let's go over these names. So right now we have 4 different compounds. I want you to take a moment, pause the video, and I want you to come up with their names. It should take just a couple minutes, right? Ideally, we want to be doing this in about 30 seconds a compound if we can. So when we're looking at this first one here is going to become our calcium oxide. It doesn't need any Roman numerals since calcium is a normal primary group metal. We should change that oxygen to oxide. Looking at our next one, this should be our potassium bromide. Then we have aluminum sulfide and magnesium chloride. Now, all of these were ionic compounds because they're all a metal and a non-metal. And then none of these were our transition metals. Looking at our next one, we should be able to identify which of these names matches with that compound. So go ahead and take a moment and do that. Now, looking at this, we have iron and we have sulfur. So we know that it's going to end in sulfide and it's going to start with iron. But iron is a transition metal, so we do need to figure out its charge. So if we're looking at this one, we know that sulfur is a 2 minus, and there's 3 of them. So that means that we need 6 minus charges. We have 2 irons, and so that means each iron must be a +3. So we are looking for iron 3 sulfide. Copper oxide, we know that oxygen is a 2 minus. And so our copper must be a 2 plus in order to balance that out with its 1. And so it should be copper 2 oxide. Now, how we find those charges of those nonmetals is we have to look at the periodic table, and we're seeing how many electrons they need to gain before they can look like an octet. We can look at our metals, and we can see how many they need to lose before they look like a noble gas. And so that's kind of how we're looking at that. So sulfur, it's in group 16 or group 6A, and so it needs 2 electrons before it starts to look like a noble gas. The same with oxygen. The fluorines, or fluorine, chlorine, bromine, the halogens, they're in group 7A. They only need 1 electron before they start looking at noble gas. So they make a charge of 1 minus. Now we have some names here, and we want to make sure that we can take these and turn them back into a chemical formula. And so for each of these, what we want to do is we want to break them down and look at each of the individual pieces. So for potassium, we know potassium is going to be a +1. Bromate, now you see how it doesn't end in I? That lets me know that that must be a polyatomic ion. So I look on the polyatomic ion list. I can find bromate as Bro3 minus. And so if I want to make a correct formula of them, I want those charges to balance. So I just need 1 potassium and 1 bromate. Moving on to our next one, calcium carbonate. Calcium is a 2 plus, carbonate is a 2 minus. And so if we put those together, we also only need 1 of each, and their charges balance. Sodium phosphate, sodium is +1, phosphate is a -3, which means that I'm going to need 3 of those sodiums, so I better put that 3 down there, to combine with 1 of those phosphates. Iron 3 oxide, iron's +3, oxygen's -2, and so that means that I need 2 irons and 3 oxygens. And then our last one, iron 2 nitrate, so that's Fe2 plus, and nitrate, instead of being NO3, it's NO2 minus. Once again, that's coming from a polyatomic ion list. And so you just want to make sure that you're using the correct one. There is a nitrate as well, but we want nitrite. And so now I need 2 of these NO2s. And how I can do that is I could double each of them, but it's easier if I just write NO2 in these parentheses and then say that there's 2 of that entire set for the NO2s. And so this is the more common way that we're going to see our polyatomics get written when there's more than one of them, is using this parenthesis system. Let's go ahead and look at these. So we want to take each of these, break them down. This is calcium here and phosphate. So we can just list that as calcium phosphate. We don't have to say anything about how many of each because we can figure that out from their charges. Now this one is going to be iron and bromide, but we can't just stop there because we do have to indicate the charge of that iron since it is a transition metal. And so looking at this, our bromide is a -1. There's 3 of them, so our iron should be a +3. And so we should use our Roman numerals for that. This is aluminum sulfide. Looking at this, zinc is a transition metal, so we are going to put its charge in there. Sometimes it does get left off because zinc really only shows up as a 2+, but it doesn't hurt for us to include it. And so there are some of these exceptions, things like silver. I will accept Roman numerals on anything that's a transition metal or a post-transition metal, except for aluminum. Aluminum really doesn't have multiple charges, so we don't want to get in the habit of doing that with aluminum. So this one should be zinc. That NO2 is still nitrite, but you can also write this as zinc 2. Now, this one's a little bit tricky because we have a lot of different pieces. So what we want to do is we want to see if there's a polyatomic that fits in that compound there. And there should be one. It's called sodium bicarbonate. Sometimes people get it confused and call it sodium hydrogen carbonate, but we can really just call it sodium bicarbonate. We have a couple more to practice here. Calcium nitrate, iron 2 hydroxide, aluminum carbonate, copper bromide, and lithium phosphate. So you want to make sure that you practice these, right? These naming of compounds, it takes a lot of practice in order to get comfortable with them. There's a lot of different rules that you have to apply. And so if you only ever do a couple of them, it will make this harder, especially because if you get these compound formulas wrong, later on when we start doing our problems with them, then our entire equation can be off because we started off with the wrong materials. It makes our life a lot harder later. So we want to make sure that we're practicing this. So calcium nitrate, calcium is +2, nitrate is -1, and so we need 2 of those. Iron 2 hydroxide, iron is a +2, hydroxide is a -1, so we need 2 of those. Aluminum carbonate, aluminum is a +3, carbonate is a -2, so we should have aluminum 2, carbonate 3, so that way they both have 6 charge. Copper 2 bromide, copper is a +2, and so that means we need 2 bromides since each bromide is a -1. And then lithium phosphate, that's lithium with a +1, phosphate with a -3, and so we need 3 lithiums for that 1 phosphate. Right? And so that's what we're doing with these naming ones. So you want to keep practicing with that. We're going to talk a little bit more about covalent compounds and acids today as well. So we showed this last week when we were talking about why our atoms bond. And so there's 3 types of bonds. We have metal and nonmetal, which is our ionic, like what we did this morning with the namings. And then we have nonmetals and nonmetals, which is going to be our covalent ones, which we'll talk about. Metals and metals form metallic bonds. And so we're going to look at each of these different types of bonds and go through them a little bit. So the first one is go ahead and draw this diagram in your notebook. It starts off with our sodium and our chlorine separately, and then it's showing what's happening to the outermost electrons there. That's what these little balls stand for. So sodium starts with 1, chlorine starts with 7, and when they form a compound, what we see is that electron really gets transferred from that sodium to that chlorine. So sodium becomes a +1 since it's lost its electron. Chlorine becomes a -1 since it's gained that electron, and then that difference in their charge is what holds them together. That positive charge attracts that negative charge. And so that's how they form. So an ionic bond is what this is called, and is between the metal and the nonmetal. And basically the electronegativity difference, so their ability to attract electrons between the two is so large that the electron spends all of its time at one element, the chlorine in this case, and not any time with the positive one, the sodium. So that means that instead of this electron kind of spending time between both, it's really just transferred from that metal to that nonmetal. And it's the attraction between the positive and negative charge ions that keeps this together. So these are very strong bonds and difficult to break. Now, this electronegativity difference that we're talking about is generally considered to be greater than 1.7. Sometimes you can see that get brought up all the way to 2.0, depending on the type of, depending on the book that you're following. Right? But that's what we're looking for. We're looking for a big difference there. And so we can see that they form these crystal structures, which is made up of these ions repeating over and over and over again. And so they form these solids here, which are very strong and hard for us to break down. Go ahead and draw this diagram in now. Now this diagram is different. What's happening here is that those electrons, instead of being transferred from one to the other, we can see that instead they're being shared. So those green ones are all electrons that start with the carbon, and the red ones are all ones that start with the oxygen. So instead of being transferred, these ones are being shared between those two atoms. So covalent bonds typically form between two non-metal elements, and that's because that their electronegativity difference is close, so the electrons end up spending time between both of those elements. We call that a bonding pair. So one bonding pair is equal to 2 electrons that are being shared. And so the bond strength of a covalent bond varies because sometimes those can be very evenly shared electrons, and so it spends time between both. Sometimes it can be a very uneven share of electrons. And so we can classify that as being polar, which is very uneven, or being very non-polar, which is going to be when they're evenly shared. And so covalent bonds, that they're sharing electrons between them. Ionic bonds, they're transferring those electrons between them. So remember, ionic bonds, taken, not shared. So when we're thinking about this, when we look at something like sodium chloride, does it have a molecule, or is it just a collection of ions? And so if we go back and we look at the picture, sodium chloride, it's not just this one green and this one purple together and that they move around by themselves in the way that we see it with this carbon dioxide molecule. It really forms this cluster because any positive will be attracted to a negative. And so if we have many positives around that one negative, we kind of form this section here. So we don't know if this green goes with that purple, or maybe it goes with that purple, because it's attracting them from all sides, and then those purples are attracting even more chlorine ions to fill in that other side of them. And so when we're looking at NaCl, it's not that one sodium combines with one Cl, it's that their ratio is a 1-to-1. That one sodium and one chlorine ion is where the ratio lies, but they really make these big, large solids with them. And so our answer should be no, it's not. Ionic solids don't contain discrete molecules, so they don't have those individual parts. This is different than our covalent compounds, right? So covalent compounds, they form these molecular solids. That means that they form a molecule, and the reason for that is that in covalent compounds, they're sharing those electrons. So because they have covalent bonds, then those electrons have to be directional. They have to be between one carbon and that specific oxygen that those electrons came from. Because of that, because they're not fully transferring them, then they're going to form their own set, their own team, right? So they're going to have those molecules there, and that's going to prevent them from just all mixing together the way that it happens with our ions. So we want to go through and want to label each as being a molecular or ionic as we're going through this. So the big part to look for is whether you're metal or you're non-metal. So NaCl is going to be ionic because it's a metal and a non-metal. H2O is going to be a molecule because it's two non-metals. And so you want to do that as you go through, right? Molecular, molecular. Now, when we get to oxygen, O2, you can think of this as being two non-metals coming together because oxygen is a non-metal. And so that's going to be molecular. Lithium sulfide, ionic. Titanium oxide, ionic. And so it's pretty straightforward. Now, we talked about our charges. And so if you were having trouble in the very beginning identifying which charges, then we have this chart to kind of help you visualize that. But we should know for each of them how to identify all of our primary groups. So that's going to be ones here and ones here. We should know what ion they generally form. The transition metals and those post-transition metals, those get more complicated. So we want to at least be able to identify these. So if we have carbon here, we should know that that's either going to be 4 minus or it could be 4 plus. But that's how many electrons it needs to transfer in order to look like a noble gas. Boron, on the other hand, we know it should be a 3 plus or it would be a 5 minus. And so we should have an idea about that part. And it's because we're always trying to get them to look like a noble gas. So just like this example last time, if we look back at the periodic table and we see where they, what element it would line up with, scandium is going to be our 3 plus. Now, what we're going to go on from today is we're going to talk about our chemical formulas a little bit, and we're going to use those to help us break that down into our masses. So we talked a little bit about this where we have our molecular formulas and our empirical formulas. So molecular formulas are where we form a molecule, and so they're always mixed of just our non-metals because they form that molecule, that team, or that set. When we have non-metals and metals, then we form these empirical formulas because they are forming these giant ionic solids, and so they're not making any molecules. Now, empirical formulas can also be involved when we have two non-metals as well, because it's just telling us the lowest ratio of them. So maybe we know how much of each element is there, but we don't know how many molecules. And so that's why we might have an empirical formula. Now, the reason why this is useful is because once we have our formulas, we can start to use our masses. So I'm going to introduce a term to us, and that term is called the mole. Now, the mole is used because inside of chemistry, instead of counting individual atoms, or instead of comparing really small masses of those atoms, we came up with a number to kind of bring those atoms and those molecules into a scale that we could then measure more easily. Now, a mole is similar to the term a dozen. A dozen means 12. In the same way, a pair equals 2. So a mole is not specifically molecules, it's not specifically atoms. It can be anything. The difference, though, is that moles are generally only used inside of chemistry because the number is so very, very large that nothing else ever really gets talked about in that scale. And because nothing else gets talked about in that scale, then that's why mole really gets tied in with chemistry. Now the value of a mole is 1 mole is equal to 6.022 times 10 to the 23 of whatever that thing is. That's called Avogadro's number. And it's on your equation sheet, but it's something that you want to make sure that you feel comfortable and familiar with. Now, to give you an idea about how big that is, if we would take pennies, we could spread them from here to the moon and cover that entire pathway from here to the moon, and all of those pathways as it orbits around the Earth, so that entire center part, we could stack those pennies up 400 high and cover that entire space. And that's 1 mole of pennies. If you had 1 mole of pennies, you would easily be the richest person in the world. Because when you think about it, 1 mole is 6022, and we still have 20 more zeros after that. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So you can see why scientific notation starts to come into play here, because it's way easier to write 6.02 times 10 to the 23 than having to write that entire number out there. So you want to make sure that you're feeling comfortable with your scientific notation. So let's practice with the mole a little bit. How many atoms are there in 1 mole of helium? So if we think about helium, and we think about 1 mole, well, helium shows up by itself, so we know that's 1 atom inside of the helium. And we know that there's 6.022 times 10 to the 23 atoms inside 1 mole. So if we have 1 mole, we can set that up just like we would any other conversion factor. And so we should get our answer as C. How many molecules are there inside of 3 moles of CO2? So we could take our 6.022 times 10 to the 23. We can multiply that by 3 because we have 3 moles of it. That gives us 18.066 times 10 to the 23. But now we have 2 options here. We could have C or we can have D. Now, one of those is going to be correct, and the other one is kind of correct, but it's not really our best answer. And the reason for that is that C doesn't have it in the correct format. Remember that for scientific notation, that value that comes before the times 10 to the whatever power, that value has to be greater than or equal to 1, and has to be less than 10. Instead of doing it as C, we should really do it as D. So D is going to be our correct answer, because instead of doing 18 times 10 to the 23, we should really adjust our value of 10 to the 23. We should make that 10 to the 24. And instead of being 18, we would have 1.8066. Okay. Now, how many moles are there in 3.011 times 10 to the 23 atoms of carbon? So in this case, we have our atoms. And so instead of multiplying by Avogadro's number this time, we're converting it into moles. So we should put the number down here at the bottom, because that's how many atoms there are instead of 1 mole. Now, the important part to pay attention to is if we divide by this, make sure that you use parentheses. Otherwise, your calculator might not do it, and divide by that second 10 to the 23, and you get something like 0.5 or 5 times 10 to the 45, right? So if you get a really, really large number, it's because you forgot to put these parentheses here, because what we're looking for is really 0.5. Now, the reason why this is important is this term called molar mass, or sometimes called molecular weight. So molar mass is how much of the substance there are in 1 mole in the terms of its mass. So it has this unit of grams per mole. And this is really why the mole was developed, was that it was able to put enough of those atoms or those molecules together so that we could start measuring them by their mass. So the formula mass of something is the mass of the individual molecule, or in some cases, just the atom. And then we add all of those together to kind of get its unit. So an example of this is H2O. So if we want to find the mass of H2O, what we can do is we can take the number of hydrogens in there, so 2. We can multiply it by the mass of that one atom of hydrogen, 1.01 atomic mass units. We can add in our oxygen, so we have 1 oxygen, and it's got an atomic mass of 16.00. And we can add those together, and that 18.02 that we get, this is the mass for one molecule of H2O. So we can break it down into all of its pieces. The idea behind it is that when we're forming these molecules, we're not losing any of that mass. The formula mass should be equal to the sum of all of its parts. That mass is not being created, it's not being destroyed, it's always going to be present there. So to find the molar mass of a particular atom, we just look that up on the periodic table. So bromine has a mass of 79.9 grams. 1 mole of potassium has a mass of 39.1 grams. When we start to get into compounds, then we have to add up the atomic weights of all the atoms that make up that compound and then scale them accordingly. So 1 mole of N2 has a mass of 2 times 14.0. So that gives us 28 grams per mole. Now on your periodic table, all of those numbers in there kind of stand for something. So that number on top, that's 6, that's our atomic number, that's the number of protons. We have our symbol there, we also have their names. That number at the bottom, that's the atomic mass, or sometimes called the molar mass. That means that we can use it as the atomic mass units per atom, but we can also use it as grams per mole. And remember that this is the average molar mass and average atomic mass for all of the isotopes. Right? So it's the weighted average. So it's, if we were to randomly pick up a carbon, we might have it as carbon 12, carbon 13, carbon 14. And so we've taken into account for that. So we use molar mass to count the molecules by weighing them. So instead of having to sit around and actually individually count molecules, we can use their mass. And when we combine it with Avogadro's number, we know how many of those molecules there are. So take this one for example. Let's say we want to figure out how many molecules of A there are. So we can take the grams of A. We can then multiply it by its molar mass. So we convert that into moles. And then we can use Avogadro's number to convert that mole into molecules. This way we can just measure this value, how much of the material we have, and then we know the number of molecules there. That's kind of what this diagram is there to help you visualize, is you can see how you can go from one to the other. We can go from atoms and molecules to moles, and then moles to grams. We can also go from grams all the way over to molecules, but every time we're going to transition through this moles part. So you want to make sure that you're paying attention to how you do that. Now you can memorize that which way you have to divide or multiply, or you can just look at your conversion factors and your dimensional analysis. If I have molecules and I want to get into grams, then I know that my molecules is some amount of moles to a molecule, right? So I can line those up accordingly. That means my molecule is going to go down here. If I want to go from into grams, then I know I want grams on top. And I know molar mass is grams per mole, so I can have mole on the bottom. And now we've lined it up correctly. We've divided by Avogadro's number, we've multiplied by grams. So you just want to make sure that you practice changing your molecules to grams, grams to molecules, and vice versa, because we should be able to adjust that. So these are some practice ones. How many moles of gold are there in 297.0 grams? So if we're looking at that, we can look on our periodic table for gold. Now gold has a molar mass of 196.9665 grams. And I got that by looking at our periodic table. In our periodic table, we find gold and we have its molar mass down at the bottom. So now that we know gold's molar mass, we can take that 297.0 grams. We can say 1 mole is 196.96655 grams. And then we can do that conversion, and we can see that we're going to be 1.5 grams. Now, if we were paying attention to our significant figures, we should be able to think about how many significant figures this should have. But right now, since our values are only given to the tenths, then we know which one it should be. But in reality, we should have 4 significant figures from our mass. We have a lot more than that in our molar mass, and so we know that this should be 1.508 moles. Now, this is a different kind of molecule. This is called a Buckminster fullerene. And so this is an actual molecule that they developed. It looks a lot like a soccer ball. Now, it's got 60 carbon atoms connected to make one of those molecules. So what is the mass in grams of one C60 molecule? Right? Now, that looks like it might be a little bit difficult. So let's take a moment. Let's break it down. We know that we have a molecule. It's got 60 carbons. So we want to first determine that's molar mass. Once we have that molar mass, we can then determine our mass of just one molecule, because we can divide it by Avogadro's number, and we can turn that mole into molecules. So looking at this, in order for us to find our molar mass, we know that one C60 contains 60 carbon atoms. We know each carbon atom is 12.01 grams of carbon. So we know this and we know this. And we know 1 mole of that is going to be 6.022 times 10 to the 23. So what we've done here is we basically taken our grams per mole, we've changed it to grams per molecule using Avogadro's number. And we've found that grams per mole by taking this chemical formula and breaking it down based on, we know that 1 atom of carbon is equal to 12.01 grams of carbon. So if we have 60 of them, then we know that that should be 60 times as big. So we can find the mass of just one of those molecules, those C60s. And it makes sense because one C60 atom should be a really, really small mass compared to a mole of them, but definitely a lot bigger than our 12.01 grams per mole, right? If we think about C60 in terms of its molecule or if its molar mass. So converting weights to moles, we just want to make sure that we are using our periodic table to get those molar masses. And then we want to multiply or divide by them. And if it's not an element, then we want to look at how many of those pieces there are inside, and we want to build them up to find the weight of one molecule. Oh, sorry, 1 mole of that molecule. So in this case, carbon dioxide should be 1 carbon and 2 oxygens. Now, how far you need to keep those numbers depends on what you're doing with them. You might need a lot of significant figures if you have very precise measurements. If you're doing some rough calculations, you might not need as many. And so you just want to make sure that you're practicing with that part, following your significant figures. A general rule is always keep at least 2 decimal places when you guys are calculating your molar masses. If you're not sure, keep at least that. Sometimes you can do more, or sometimes you will need to do more, especially if your numbers have a lot of significant figures in them. So how many atoms of uranium in 0.5 moles? How many moles are there in 120.11 grams of carbon? How many atoms of carbon are there in 1.2 moles of carbon? So how many atoms of uranium in 0.5 moles? So we have 0.50 times 6.022 times 10 to the 23rd equals 3.011 times 10 to the 23 atoms. And if we wanted to pay attention to those significant figures, our moles is 2. And so this should be 3.0 times 10 to the 23 atoms. How many moles are there in 120.11 grams of carbon? Now we know 120.11 grams. We know 1 mole of carbon is 12.011 grams. And so we would get 10 moles. And if we use our significant figures, we should have 5 of them. So 1, 2, 3, 10.000 moles. How many atoms are there in 1.2 moles of carbon? We take those 1.2 moles. This time we should multiply it by our 6.022 times 10 to the 23. We get 7.226 times 10 to the 23. Looking at significant figures, we should only keep 2 of them. 7.2 times 10 to the 23. And in this case, this would be our atoms of carbon. And so it's always a good idea to write down what you have instead of just atoms. We should write down the elements and the moles, because you're going to be working with a lot of things, and they might come up with a lot of different moles or a lot of different atoms. So in summary, your atomic weight you guys find on the periodic table is equivalent to the mass of 1 mole of that atom in grams. The molar mass of a compound is the sum of the atomic weights of all of the atoms in the compound. And the molar mass allows you to convert between moles and grams. So go ahead and pause this video here. Determine the molar weights or molecular masses of the following compounds. So sometimes they're called molecular weights. They're also called molar mass. Those are the same things. They get kind of used interchangeably. Weights is not quite as good as masses, because mass doesn't depend on a gravitational pull where weights do. Here are the answers for them. We have 14.007. That's our nitrogen. We have 3 of the hydrogens, 1.0079. So we should be 17.031 grams per mole. Our carbon, we have 3 of them. Hydrogen, we have 8. Give me this 44. 2 lithium, 1 oxygens, 2 irons, 3 oxygen, right? And so we have that as we go through. How many atoms of NH3 do you have in 34 grams of a sample? Now, I realize that this was poorly written. We should just call this molecules. And that's because NH3 doesn't show up as an atom. An atom implies that it's just one of those nitrogens or one of those hydrogens. We really have them showing up as a team, which is how it's being discussed. So I'm asking for how many molecules of NH3 do we have? And we are looking for D. And how I got that was I found my molar mass of NH3. So that's the grams per mole of NH3. I took my grams. I divided it by my molar mass, and that tells me my moles. I then took those moles and multiplied it by my Avogadro's number, because that's my number of molecules in 1 mole. Now, in shorthand, you might shorten moles to just MOL. There's not really any acceptable shorthand of molecules, so just be careful about using MOL. Don't use that for molecules. It stands for moles of material. Now, all of this, what we've been doing, is this introduction to something that we're going to call stoichiometry. And so I would really recommend that you take a page from your notebook, near the front or the back, and create this island diagram. Now, what we're going to do with this later on is we're going to add more and more pieces into this as we do these conversions. Now, a lot of chemistry is actually just conversions of that material from one piece of information into another. So it might take the mass of something, turn it into moles. Or it might take the mass of something and turn it into the moles of something to turn it into a different material through a chemical reaction into something else. And so over the course of this semester, we're going to keep adding more and more of these islands to it. Instead of just using our mass, maybe we're going to add in a volume, liters. Like already, for our mass, we can add in something. We can have it as molecules, because we can use the Avogadro's number to turn all of our masses into moles, but we can also use those moles to turn them into molecules. So I guess maybe instead of drawing it up there, a better one would be to go off of moles into molecules. Or we can do it into atoms. So we're going to eventually add more and more of these islands in here, so that way we can do more and more of these conversions. So it's just a way to help you visualize those pathways as you work through it. Let's think about what the molar mass of calcium phosphate is. Now, when we think about calcium phosphate, you first want to change that into its chemical formula. If you don't have the chemical formula, you won't be able to figure it out. So we should have calcium phosphate. Now, we can't just stop there because their charges aren't balanced. So we have 3 calcium and we have 2 phosphates. Now, what that looks like is that means that we need 3 times the calcium. We need 2 times phosphorus. And we need a whopping 8 times our oxygen. So that's why these values are so big, is we have to make sure that we're scaling them all correctly. And so that's going to give us 310.18 grams per mole. We're going to look at sulfur dioxide and our caffeine here. Now, sulfur dioxide, this is a covalent compound, 2 nonmetals. Right? And so that's why its name is a little bit different. Instead of using our metal-nonmetal strategy, we have to use the one where we use our number. So we need to use di in order to say that there are 2 oxygens. Remember, SO would be sulfur monoxide. And then caffeine. And so for both of these, we want to find our molar masses. So for sulfur, we can break that down into 1 sulfur and 2 oxygens. For the caffeine, it's a lot more going on, but we can still break it down the same way. We have 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens in order to get our molar mass for that. So you can call those AMUs. You could also call them grams per mole. Either one would be fine. And so for the very last thing, what I want you guys to do is go ahead and look at our sample here and decide which of these represents the greatest number of moles. Now, in order to compare them, you can't leave them as grams, moles, molecules. What we need to do is we have to get them all into moles. So get everything into the same unit first, and then we can compare between it. There's a saying, you can't compare apples and oranges, right? That idea is that if they're not the same unit, we can't really compare their values because their conversions could be different. So we need to convert them into the same unit so that way we can compare their values. So we need to convert all of them into moles in order to compare that. So CO2, we can use our molar mass to convert that into moles. That ends up being 1 mole This is already in moles, so we can leave that. This one we use Avogadro's number, which gives us 1 mole. Water, we can use our molar mass to get there into 1 mole. And so all of these have the same number of moles. They're just expressed in different ways. So we'll be working a lot more with moles and molar masses as the semester continues. So make sure that you practice with that. If you guys have any questions, make sure that you guys ask.